All right, let's go to nearest neighbors. So you saw this in Pedro's lecture of the idea of an analogizer, right? Which is to compare something like a data instance with something else to assist our understanding, right? So we can say, oh, if this data instance seems very similar to another data instance, and I know that other data instance is actually a yes value, like something that the person likes to drink, or considered a weather forecast in which we had played golf in the past, we are going to make the analogy that by this type of similarity, we believe the other case will also take the same class value, right? So we're going to assign a test instance to its closest neighbor. And to do that, we're going to memorize the training data and then compute which training instance is closer to the test instance. Okay, it's a very simple idea. We do it all the time. Okay, so to recap this, let's take a look at image classification. Okay, this idea that we wanted to take a look at pictures of cats and dogs, for example, and classify whether the animal that you see is a cat or a dog, right? So recall that we have an image of a cat. We can think of it as pixel values. Okay, so we have all these millions of particular numerals for the RGB channels of an image. Okay, and we want to take all of these 1.44 million integers and decide whether another 1.44 integers from another image is similar or not. Okay. So we're going to introduce this CFAR dataset, which is basically a set of these types of images. Okay, they're cut into 10 classes. So the classes come from images that people found on the internet. So planes, cars, birds, cats, all the way to vehicles like trucks. Okay, and they just crawled images from the web, they assembled them, looking at, for example, the image captions of the image captions that it was a truck. They just assumed that the image was a truck, and they compile these test data set sort of semi-automatically. So you have gotten 50,000 images for training, which are labeled, and then they took labels away from 10,000 instances, and they called that their test set. Okay, so you can see things of this sort here. So you might see some of the things are actually not correct, but more or less they're all okay in this picture. Okay, and so what we want to do with the nearest neighbor algorithm is use images perhaps from the CFAR dataset, right? And then try to see whether we can build an image classifier. And one way simple to do that is to use a nearest neighbor algorithm, which we are going to define what is the distance between two different pictures, right? So that is the key in which nearest neighbors computation needs. And a very simple way to introduce this idea is to use what we're going to call the L1 distance metric. Okay, so there's a formula here. It's actually fairly easy to understand. It says the distance calculated between a particular test image, this is what our star is, and a particular image in our training data set. So this is the actual first instance in our training data set. Okay, this X in parentheses 1. Okay, so this is the first row of our data matrix, is going to just be equal to the sum of the differences. Okay, the sum of the differences between a particular pixel P, so ranging over all 1.44 billion, million pixels. Okay, so we're going to assemble all of the pixel differences between the pixel at a particular point in the test image and the same pixel in the training image, and then take just the absolute value of differences between that. Okay, so to show you this, we can expand, let's say, the upper left-hand corner of an image and say for our particular training image, our X1, we have these values over here. And then for a particular testing image, we have these values over here. And all we're going to do is compute a pixel-wise absolute difference, right? So then we can pick any one of these. So for example, this 26 here and this 16, they are correspondent, they're in the same places. We're just going to subtract them from each other and put the absolute difference in the corresponding cell. And we're going to do that for all 1.44 million and then add them all together. So in this small grid of 16, there are 456 different pixel differences. Okay, that's what we're going to do. So when we want to visualize how nearest neighbor works, we can calculate all of these individual features, right? So we have, let's say, 1.44 million different features, which are the pixel values for each individual one, okay? And let's take 2 pixels, okay, and then plot their values, right? So we can go back and say, oh, let's take the 10 and 20 here from the training image, and then use the 10 as the x-axis and the y-axis is the 20, and plot a dot. Okay, so that dot is going to be on this grid, and we're going to put all of the training instances, the top 2 pixels, their values, and then put them on this grid. Okay, so the red ones might be all of the cat images, the blue ones might be all of the dog images, and the green ones could be a third class, let's say trucks. Okay, and you can see what we're doing is we're going to say that those 2 pixels somehow describe where all of these different images are, right? So we might get clusters because the images of one class look similar to each other, so the pixel values might be similar, okay? And if we colorize all the dots, we can plot out a space, right? And so on the left-hand side, we have the dots plotted out. On the right-hand side, what we've done is colorize the rest of the intervening space. You know, we don't have enough images to tile the whole space of all possible values of these 2 pixels, right? But if we can see where the nearest single neighbor is to a point, we can colorize the rest of the space. So here, this particular point over here means that this blue dot in the middle of that sort of quadrilateral there is the nearest point for all of the possible pictures that are in this confine, okay? And then likely similarly for the rest, right? So all of the green regions here, it means a green image, or perhaps a cat image if cat images are green here, is the closest class. Okay, and the way we can understand this is it's actually like a Voronoi tessellation. So if you've done some geometry work here, then think of these different points here as image samples, okay, which we have from our training data, and we are just drawing the boundary, right? It's a polygon boundary between all of the points, right? So between any 2 points, let's say this point here and this point here, we're going to draw the straight line connecting them and taking the perpendicular bisector that's equidistant from both parts. That is the boundary, right? So any point that's, let's say, over here is a little bit closer to this point, so it's going to be colored whatever is that point is colored. And any point on this side of this boundary is going to be colored the same as this point down here. Okay, and we're going to define this surface for all of the other points that are in the training data set, and we're going to get this tessellation, right? This nearest neighbor boundary, which is very complex because it has a lot of straight line segments that's going to define the boundaries between our classes. So using this particular algorithm, imagine that instead of having a 2-dimensional space, we have a 1.44 million dimensional space, okay, in which we're doing this huge tessellation, okay, and we are taking a new sample image, okay, a new test image, and putting it somewhere in that space, okay, and we're saying, okay, what is the nearest point to that particular test instance, okay, whatever it is, I'm going to call that point the same as the nearest point, okay? And you can see what that comes out with. Here we have what looks like a truck, and it came out with things that look like looks like a horse, another truck, which might have taken from the same video or something, a car, etc. So it makes some mistakes. So this is ordered from most probable to least probable. So it's least over here and most probable on this side. And you can see that the test images actually sometimes work, sometimes don't. So you get a cruise ship looking like a cruise ship, a sailboat looking like another, looks like a flipped over sailboat, a horse looking like a deer, etc. So some of them are correct and some of them are not. Okay, so in summary, for nearest neighbor, this is an interesting algorithm because it's parameter free, right? There's no distillation of actual tuning things that we need to worry about, okay? It does have a meta hyperparameter, which is the number of nearest neighbors that we want to go into consideration. But for the purposes of this pre-lecture, we only considered the nearest single neighbor, okay? And it does actually require an immense amount of time to apply because we actually have to cycle through all of the test data. We have to go through all of the images that we have in our test, put them as a point in this space before we can calculate which one is the nearest neighbor. Now we want to be able to, of course, be able to speed this up if possible. And we notice that this doesn't really work well in high dimensions. And even if in this case we have 1.44 million parameters, you can see that some of them are not done properly. And I'd like you to think about why this particular algorithm doesn't work well in high dimensions. We're going to explain that in our post-lecture, but for right now, give it some thought before you watch the post-lecture on the curse of dimensionality.